All right, so there are several ways in which we can integrate this SIR model. And some of those extra ways are given in the homework, so I won't get into that. Let's go over one typical way to do it. So as it turns out, and that's a rare treat, as I said before, we can separate the equations. So if I divide, so notice that I can write I prime as di dt and s prime as ds dt. So if we divide the two equations and do a little bit of algebra there, so I can simplify I can pull out I on the first equation, crosses out, and then if we rearrange the terms, that's minus 1 plus r over lambda 1 over s. So dt cancels, and we can write essentially the whole equality as two differentials equal to each other. So 1 times di on the left, think of the left side as a differential in I, and the right-hand side as a differential in S. Even if you didn't go through the separation of variables, it's easy to follow from this point on because the method consists in integrating both sides. So that if you have essentially this the equality of two differentials, that means the two original functions differ by a constant. So you can integrate both sides, on the left side with respect to I, on the right side with respect to S. One thing to keep in mind with these notations in the math biology is to not confuse S and I with the initial values, right? So by S, I really mean S of t. By I mean I of t. So when the time comes to plug in 0 for t, you won't see explicitly t replaced by 0, but you will see S replaced by S naught, I replaced by I naught, because under that assumption, we replace t with 0, so we look at the initial conditions. So the left side is just I, the integral of 1 di. The right-hand side is minus s plus r over lambda, natural log of s. And plus a constant of integration. So let's pay attention here, because this constant of integration comes from initial condition. So after I replace t with 0, this whole equality becomes I naught equals minus S naught R over lambda ln of S naught plus a constant C. So the constant of integration that I'm to replace with on the left side is given by this. So replace it back on the left side, and the full equation that relates S and I becomes this one. And just to make stuff a little bit better from an aesthetic perspective, just to make it look a little bit more organized, let's move S on the left. So S plus I. We can combine the two logarithms into natural log of S over S naught. That's properties of logarithms. And S naught plus I naught. Again, pause for a moment if needed and make sure you really understand that what I just wrote here is just shortcut for S of t plus I of t equals R over lambda ln of S of t over S naught plus S naught plus I naught. It's very important to understand what gets to be a function and what is a constant in all of these in this relation. For convenience, we don't write S of t, I of t all the time, but these are functions of t. So it doesn't look like too big of a deal in the sense that we are able to integrate it, but it's not like, unfortunately, it's not like we could actually solve explicitly for S and I. So maybe surprisingly so, even this simple model doesn't allow you actually to solve explicitly, so you can tell what S of t, I of t, R of t is equal to at any time t. The best we could do is to relate two quantities. Doesn't have to be S and I. You can do I and R, or I think S and R as well. So you can combine any two of them and relate them with some equation like this. But that's the best you could do, right? You could have basically a relationship between S and I. We won't be able to tell what S of t, I of t is separately. But it's still quite a lot in terms of what we can do with it. remember what we said before, that we know that I of t approaches 0 eventually. So that means as t goes to infinity, I can find the final size of S and R by default, right? Because remember, the population is constant. So let's say the total population, just to use an example as before, is 102, right? I mean, imagining that we start with 100 susceptibles, 2 infected, and obviously no recovery yet. Because I know that eventually t goes to infinity, I goes to 0 if t goes to infinity, then I can go back in the relation between them and replace I with 0 and solve for S. So the final size of S is denoted by sometimes by S infinity. I don't want to bother you too much with this extra notation. Is that it's important to, again, put some accent or some hat or some star of some sort, just to not confuse it with S of t. So when I replace y with 0 in the equation here, I'm going to end up with S equals R of lambda ln of S over S naught plus S naught plus I naught. I'm going to show you a couple of examples on the second page. And when you get to solve S by itself, you really solve for final size S infinity, not for S of t. So you will find basically a constant which denotes the final value of S of t when the epidemic is over. So when I of t goes to 0. This cannot be done by hand. We have to use Maple or Wolfram Alpha or some other computational tool to solve for S. And we always have to pay attention that the solution makes sense, because it has to be constrained by the total population, which is 103 in this case, in my examples that I'm going to show you with Maple or something similar. So I'm going to go over a couple of examples that I'm going to run with Maple as well in the last part. But once again, remember, we can find S of t, I of t explicitly. We can only find the final size of S if we replace I with 0, because we know a priori that I of t goes to 0 eventually. So let's do it on the same part here. I'm going to copy so let's actually choose some values which I actually computed before. So suppose yeah, so let's say again that the initial population for susceptible is 100, I naught is 2, R naught, the initial value of R is 0. So the final size equation for S will be S plus 0, that's just S, R over lambda ln of S over 100 plus S naught plus I naught, which is 102. So let's play now with some examples in terms of possible values for R and lambda. So let's say lambda is 0.02 and R is 0.5. So you can check this for yourself. Plug in these values, solve it with Wolfram Alpha or something similar, and you will notice that S final is going to be 2 or close to 2. It's not going to be precisely 2, but approximately 2. How many susceptible are to begin with? 100. That means 98 were infected. Makes sense. 0.5 for R is pretty low recovery rate. If I increase the recovery rate, I should get better numbers in terms of people being infected. Let's say lambda is 1.0, and again, replace it in the equation. Check that the final size of S is going to be close to 19, which means 81 infected. And let's be even more optimistic. Suppose that R is equal to 3, much bigger recovery rate, and still keep the infection rate 0.02. Final size for S in this case, don't just believe me, try to run this number yourself, and I'll show you actually with Maple later. Final size of S is 96, which means a very fast epidemic that went over very quickly. So 4 infected, right, from the original 100 people. So stay tuned for the last part when I'm going to show you some simulations over the computer. And also I want to illustrate also an example with the meaning of R naught when it's greater than 1, less than 1, and how the solution plays out, how the behavior of the equation looks like in that case. So that's it for today. Again, stay tuned for the very last part, and then that'll be it for this week.